Sight, a precious gift we can't take for granted. Our eyes are windows to the wonders of the world. All we know and love, experience and discover, ponder and cherish. Let's peer into the workings of the eye, a unique and self-sustaining system. The reflected light of the world enters through the crystal transparency of the cornea, aqueous humor, lens, and vitreous humor to project onto the photoreceptors of the retina, whose impulses converge on the optic nerve, and then to the brain to be transfigured into imagery and imbued with meaning. Continual adjustments to the pupil and lens regulate the entry and focusing of light. In today's world, the eye's surface is constantly challenged to protect itself and adjust to changing conditions. Every blink helps our eye's natural defense system, the tear film, retain moisture and maintain visual acuity. Tears contain potent natural disinfectants to keep bacteria at bay. And the tear system washes away impurities to maintain eye health. The miraculous biology of our eyes inspires us to develop ways we can protect and maintain comfort for these remarkable structures. For all the wonders our eyes provide throughout our lives, we owe them our attention and ongoing care.
The ear has three parts: the outer ear, or auricle, the middle ear, and the inner ear. The auricle, the visible part of the ear, collects sound waves and directs them to the auditory canal. The auditory, or ear canal, is lined with cilia and ceruminous glands. The earwax from the ceruminous gland and the cilia protect the ear from entry by foreign matter. The thin tympanic membrane separates the outer ear from the middle ear. Sound waves cause it to vibrate. The three tiny bones of the middle ear are the hammer, or malleus, anvil, or incus, and stapes, or stirrup. These bones pick up the vibrations from the tympanic membrane and transmit them to the inner ear. The eustachian tube of the middle ear opens into the pharynx and permits air pressure to equalize between the ear and the outside air. The inner ear is maze-like, consisting of bony and membranous structures surrounded by fluid. The semicircular canals are fluid-filled bony loops that help maintain our body's balance. The cochlea is a fluid-filled, snail-shaped structure that houses the organ of Corti, the true organ of hearing. The fluid aids in the transmission of the vibrations. The organ of Corti changes the vibrations into nerve impulses that are picked up by the auditory nerve. Sound waves are collected by the auricle, or outer ear, and sent to the auditory canal, tympanic membrane, ear bones, and then to the cochlea, where the vibrations are changed by the organ of Corti to nerve impulses and transmitted by the auditory or cochlear nerve to the temporal lobe of the brain for interpretation.
The body's largest organ, the skin, serves as a protective coat, guarding internal structures from the outside environment. It is composed of two distinct layers of tissue, the epidermis and the dermis. The epidermis consists of an outer sheet of dead cells called the stratum corneum. and a deeper section of rapidly dividing cells called the basal layer. When dead cells of the stratum corneum are damaged or scraped off during body activity, cells from the basal layer rise to replace them. The epidermis serves as the body's initial barrier to invading foreign substances. Directly below the basal layer is the thicker dermis layer, made of dense connective tissue. Embedded within the dermis are several kinds of important sensory receptors, including thermoreceptors, which detect temperature change, Meissner's corpuscles, which are sensitive to touch, and free nerve endings, which detect pain and tissue damage. The dermis also contains many other structures, including sweat glands, hair follicles, and blood vessels.
In the past, the sense of smell has been a great mystery to many scientists. How does the human body distinguish between the aroma of cookies baking and perhaps the more dangerous smell of something burning? It is questions like this that have driven scientists to uncover the cause of such odors: airborne molecules. As we sniff to distinguish a particular odor, molecules emitting from the substance travel through the air. The size of the molecule affects how far the odor can travel. The lightest molecule will travel the farthest. Scientists refer to this occurrence as volatility. Once the molecules enter the nose, they travel into a small patch of tissue called the olfactory membrane. The olfactory membrane is very small and located at the top of the nasal cavity. The membrane is made up of yellow-gray tissue and covered with a thick mucus. Within the membrane are many receptor cells, which are considered to be extensions of the brain itself. It has been theorized that each receptor cell is sensitive to the dimensions of a particular molecule. Once the correct molecule has been attached to the matching receptor cell, a nerve impulse is created. The nerve impulse will continue to the brain through a thin bone in the forehead called the cribriform plate. Beyond this plate lies the olfactory bulbs, where the nerve impulse will make its first junction with the brain. In the olfactory bulb are many structures called glomeruli. The primary function of these structures is to distribute the converging nerve impulses to the brain in an orderly fashion. In the brain, the impulses are scattered to different areas, where they are decoded and odors perceived. Scientists have determined that the human brain can identify between thousands of different odors. Thus, it is safe to say that the sense of smell is one of the most remarkable assets of the human body.